Okay, well, I hope everyone's doing well. This is ninth week of the class, so this is kind of our last week of heavy content, I would say. Okay, next week we will cover a little bit of new stuff, but it'll be very, in my opinion, lightweight material. Okay, and then. And then the week after that will be review, and then the week after that will be the final exam. Do we have a question?
So the final exam is on the 14th, correct?
June 14th, correct. Okay. Now,
7 p.m. Sorry.
it will be 7 to 10 p.m. Yes. Yeah.
We don't have a quiz on the class before the final, right?
Yep.
So we have one more quiz.
No, we do. We have two more quizzes. Yeah. We have two more quizzes. Total of 8 quizzes. I will drop the lowest of the 8 quizzes. Okay. And yeah. So we got today was quiz 6, and then next week will be quiz 7, and then the week after that quiz 8. Yeah. Okay. Okay. We'll it'll be good. Okay. All right, so today we're covering chapter 9, and we will do statistical inference. Statistical inference for numeric variables. That is the topic of the day. Okay, and as far as the stuff we've covered so far in chapter 7 and chapter 8, it was all dealing with categorical variables. Is that a question? Yeah.
Are you gonna have a video on those practice quizzes?
I don't know.
They are helpful.
Okay, well, I'm glad they were helpful this past week, but yeah, I mean, I don't know, no promises, okay? All right, so this week we've got statistical inference for numeric variables. So whereas before we were dealing with categorical variables, so we were dealing with proportions, okay? So with categorical variables, we deal with proportions and the z-table. Over here, we are going to have numeric variables, and we will be dealing with means, and we will use the t-table. Okay. Now the way the t-table works is very different from the way the normal table works, the z-table works. Okay. But you should kind of keep this in mind. Okay. So this is very important. If you've got categorical variables, you'll always be dealing with proportions, and you'll always be using the z-table. If you got numeric variables, you'll always be dealing with means, and you'll always be dealing with the t-table. Okay. So don't mix those up. Sometimes students will do stuff for means and then try to look up the number they find in the z-table, and that will not work out. Okay. So when you're dealing with means, you're going to look up stuff in the t-table. Okay. And so as far as inference stuff has gone, there are basically going to be 4 topics that I'm going to cover today, but they're all very, very much related to each other. So you know, it's a lot of information and a lot of stuff coming at you, but at the same time, you know, they're all kind of related. So I'm hoping I can present it in a way that's that makes sense, okay? So we will have confidence intervals. For mu based on one sample. Okay. This is mu. It's the population mean. It should be familiar from like chapter 6 when we were dealing with the normal distribution. Okay. All right, and then we will also have hypothesis tests. For mu based on one sample. Okay. We will have confidence intervals. Again. But this time it will be for mu1 minus mu2 based on two samples, and we will have hypothesis tests. Mu1 and mu2. Based on two samples. Okay, so we're going to we'll work through all four of these topics here. All today. I'm glad. Thanks for the enthusiasm here. Yes.
Is that where Pokemon got like Mew and Mewtwo from?
You know, I don't know if that's where Pokemon got Mew and Mewtwo. I would.
Because everyone else has like a different name, like an evolution.
Yeah, you know, but I don't. You know, Mew is just like the letter M, so I can't imagine the thing. And the Pokemon, they spell it M-E-W,
Oh, they do?
and this is spelled M-U. I'm thinking Mew. It's like the way a cat sounds, but when you're yeah, exactly. Yeah. Anyway, those were the days, huh? Well, I mean, now you have to capture like 700 of them. There's too many, yeah. Original 151, right? Okay, 151. Okay, so let's work through these. Now, when you look at your textbook and you do the homework, it's going to ask some questions about the sampling distribution of X bar and things like that. Okay, so I'm going to just kind of briefly cover that here. Okay, and so if you recall, what is a sampling distribution? That's right. The sampling distribution is the distribution of the sample mean X bar if we repeatedly take many samples out of the population. Okay. Okay, this is.
Is this just recap or?
This is not recap, but it's so a sampling distribution is the distribution of a sample statistic, and before it was p hat, it was the distribution of p hat if we repeatedly took samples out of the population. Like, you know, you took a scoop of Reese's Pieces candies and we counted what proportion was orange and things like that, and we did that over and over again. Okay, this time it's instead of taking Reese's Pieces, we're going to be taking I don't know, a scoop of something. All right, so maybe it's pieces of candy, but this time we're not interested in a categorical variable like the color of the candy, but maybe this time we're interested in the weight of each candy. Okay, so we take a scoop of random candies out, and then we weigh each one. Okay, and we're going to get the average weight of, let's say, a scoop of 20 pieces of candy. And for each sample, we record the sample mean x bar. Okay? So this is the distribution of x bars if we repeatedly take samples from the population. Okay, so the idea here is, we have a population. So it could be, like a tub of candy. But this time, the thing we're interested in is a numeric variable. Okay, so we're going to take a little piece out of the population. This is our sample. And the thing that we record from the sample will be the sample mean, x bar. Okay? And we do this over and over and over again. So we take another sample and we record another x bar. And we go and we take another sample and we record another x bar. Okay? Does this sound kind of familiar? Okay? Except before we were every time we recorded the sample proportion, this time we are recording the sample mean. That's the only difference. Okay? And with the sample mean, we're going to look at the distribution of x bars. Now, when we looked at the sample proportions, we said the sample proportions can be approximated by what distribution? The normal distribution, right? So we said the p hat can be approximated with the normal distribution. Well, if we look at the sampling distribution of x bar, the same thing happens, okay? The sampling distribution of x bar ends up having a normal distribution, okay? So this is the distribution of all the different x bars that you will observe. Okay, so this thing is normal, okay, and it has a mean equal to mu, which is the population mean. So the mean of the population, and it has a standard deviation equal to sigma divided by the square root of n. So this is sigma is the population standard deviation, and n is the sample size. So what this says is that when you take a bigger sample, the spread of the x bars becomes smaller and smaller. Okay? And so I can kind of illustrate this with another computer simulation here. Okay, so here we would say x bar comes from a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n. Okay. So I'll let you guys write this down, and I'm just going to kind of quickly demo the concept here. Okay, can you guys see this okay? Yeah. right, so what we're going to do is I'm going to take a sample of 10 things, okay? So this is, right here, I guess we'll just start off with samples of size 2, okay? So here, this is the population. This is the numeric variable. The population has a mean of 16 and a standard deviation of 5. This is the distribution in the population. It's a numeric variable, okay? And I'm going to take samples of size 2. So I'm going to just draw 2 values out of the population. Okay? So these 2 values, I drew something like, I don't know what this is, like an 8, and this is like a 12 or something. I don't know. I'm just making this up, okay? And then we take the average of these 2 numbers, and that's right here. That's this blue dot. Okay? I do this again. I take 2 random values out of the population. I average these 2 numbers, and then we get a blue dot right here. Okay? I'm going to do this again. Another 2. The average right there goes right there, okay? And then so I can just do this over and over again. The average of these 2 ends up right there. And the average of these 2 ends up right there. Okay, so this is just doing 5 more. Here's another 5. Okay, so we're just going to take 5 at a time. And we can see some of these values are more common than others. Here's after 10,000, 20,000. And you know, after doing this a bunch of times, we see that the distribution of the averages, remember these blue dots are the averages of 2 values. We see this thing follows the normal distribution here, okay? And we see that the spread of this thing is a little bit narrower than the spread of this thing, right? Okay, what happens if I take samples of size 5? Okay, here I'm going to take 1, 2, 3, 4, 5. I'm going to average these 5 numbers, and that ends up right there. Another 1, 2, 3, 4, 5. I take the average of these 5 numbers, and that ends up right there. 1, 2, 3, 4, 5. The average of these 5 numbers ends up right there. 1, 2, 3, 4, 5. The average of these 5 numbers ends up right there. Okay? And I can do this, you know, several at a time. And we can see after many repetitions, we get a normal distribution, but it's quite it's a lot skinnier. Okay, the spread is smaller. Okay. If I take samples of size 10, what happens? Okay, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the average of those 10 numbers is right there, okay? And we're going to take another 10 numbers. The average of these 10 numbers is right there, okay? And I'll just do this animated one more time. We're going to just taking 10 numbers out of this population, and the average of those 10 numbers is right there, okay? And then again, we can just do this quite a bit, okay? And then so after many repetitions, we're still getting a normal distribution, okay? And this time the spread is even less, okay? So again, just kind of comparing the spread after with samples of size 2 versus samples of size 5 versus samples of size 10, we can see that the spread gets smaller and smaller. And then the computer allows me to go up to samples of size 25, and if I take a bunch of those, it still ends up following the normal distribution, but the spread is a lot smaller, okay? Here the population, the original population was normal. The interesting thing is that the original population could be something that's not normal. So here it's uniform, meaning all of the values are equally likely to appear, okay? So if I do 2 values at a time, I could get something like this. And we're just taking averages of these 2, okay? And after 100,000 repetitions, we get something. This does not look normal, okay? That's with samples of size 2, okay? We can do samples of size 5 and repeat this, and after 100,000 repetitions, this actually starts to look normal, okay? And then with samples of size 10, now we've got something that definitely looks normal as well, okay? But it's interesting that when I only have samples of size 2, I get something that's definitely not normal looking, okay? And let's just take a look at what happens when I have a skewed distribution, okay? With a skewed distribution, what that means is values down here are more likely to appear than values over here. So when I, animate this, it's more likely I get values kind of in this region, and I don't very often get values over here, okay? And so just kind of doing this many, many times, after many observations, I get this kind of shape, okay? So this is not normal looking. That's still skewed. This is samples of size 5, and we can see that, that it's starting to look a little bit more symmetric. Samples of size 10, again, we still have a tiny bit of tail, but it's starting to look a lot more symmetric, and then at samples of size kind of 16-ish, it's starting to look quite a bit more symmetric here and more normal looking, okay? And we can also just kind of have, the parent population could be very much bimodal or something like that, okay? And so with something like this, it's quite possible for 2 values to appear down here, or one value to be from here and one value to be from here. And then so if we do a bunch of these, we end up getting this kind of camel looking thing where this is like both came from here, one came from over here, and one came from over here, or both came from down here, okay? And so we get this weird shape. If I increase the sample size to 5, we still get these kind of funny lumps here. But then what happens when I increase to samples of size 10? They all kind of just start merging together, okay? And we end up getting something that looks like the normal distribution still, okay? And so this is kind of the central limit theorem at play. And it just says when we look at the sampling distribution of x bar, it's going to end up looking like the normal distribution. But we have to say star asterisk as long as our n is large enough, okay? Because if the sample is small, like if you're taking samples of size 2, we saw that you didn't necessarily get a normal distribution, okay? Okay, and so as far as it comes, we still have to check for conditions to use the central limit theorem, okay? So I'm going to flip to the next page, okay? So with numeric variables, we still have to check check the conditions to use the central limit theorem. Okay, and so the conditions are the same. Okay, one is we have the random and independent condition. How do we check to make sure that this is met? The sample must be obtained randomly, right? Okay. Okay, I'm going to skip to quote unquote condition 3, which was the big population condition, because this is the same as before. How do we check to make sure that the big population condition is met?
Multiply the sample by 10.
Yeah, so the population needs to be at least 10 times bigger than the sample, right? Population size must be at least 10 times the sample size. Okay, All right, so condition 2 is the large sample condition. And this is the one that changes when it's numeric variables. So with categorical variables, how do we check? You need 10 successes and 10 failures at least, or n times p has to be bigger than 10 and n times 1 minus p has to be bigger than 10. Okay? For numeric variables, large sample, what we have is if the population is normal, any size sample is fine. Okay? But if the population is not normal, so if the population is not normal, so either skewed or something like that, for example, skewed or something, then the sample size must be bigger, okay? Now we don't have exact rules. In general, n greater than or equal to 25 is big enough for most situations. But it's also possible got an extra T in here. It's also possible that 25 is still not large enough if your population is extremely skewed or something like that. Okay. But I mean, as far as the conditions go, they're the same. Random independent, large sample, big population. And random independent and big population, those you check the same way as before. The only change is now for large sample condition when you got a numeric variable, either the population has to be normal or your sample size should be larger, like 25 or more. Yeah, question?
We know it's normal. Are we looking at it?
Yeah, it's hard to say, okay? You just kind of have to either have to go off of information that's provided, such as, you know, maybe in the problem, or someone will tell you that they suspect that the population is normally distributed. Other times you just look at the data and you say, does this data look like it's coming from a normal distribution? And you're just kind of guessing there. Okay. If you have an outlier and you have a small sample size, that would be a good indication that your population is not normal if you're getting some kind of extreme outlier. Okay, so that's sampling distributions. So if we apply kind of the same conclusions that we made from sampling distributions for proportions to numeric variables, then we can do all of that stuff with confidence intervals and hypothesis tests. So let's see, do we recall how to make a confidence interval for a proportion P, for a population proportion P based on a sample? Okay, so you guys were just, you took a quiz on this like last week, okay? How do we make a confidence interval for P? What goes in the middle of the confidence interval? Okay, so in the middle we put our best guess of P based on our data. And what is that? P hat, exactly, right?
Yeah, plus and minus margin of error.
Yeah, okay, and then we go plus or minus the margin of error. So we have p hat plus or minus. How do we make the margin of error?
The Z star table,
Z star, okay, and then we multiply that by
standard, sorry, not, yeah, standard error.
the standard error, which was the square root of p hat times 1 minus p hat over n, right? So here we have the critical value times the standard error. Okay, and we used p hat. Why did we use p hat instead of p? Yeah, but why would we use the sample proportion and not the population proportion? Because we don't know p. Okay, we used p hat because we don't know p. Okay, so I'm hoping this is kind of at least somewhat familiar. Yeah? Should be. Okay, so we will set up a confidence interval for a population mean in a similar way. Confidence interval for a population mean, and what is the symbol that we use for the population mean? Okay, mean mu based on a sample. Okay, so in the middle, what will we put? We will put our best guess for mu based on our data, and what is our best guess for the population mean based on our data? It's our sample mean, x bar. That's going to go right in the middle. Does that make sense? All right, we're trying to make a range of plausible values for what the population mean is, and right now the only information we have is what's in our sample. So it seems to me that the best guess we have for the population mean based on our sample is the sample mean. Okay, and then we will go plus or minus a critical value times a standard error. Okay. All right, and so the difference here is that because we're dealing with means, our critical value is going to come from our t-table. Okay, so we're going to call this t star. It comes from our t-table rather than z. And our standard error, what was the standard error just on the previous page for the sampling distribution? So just earlier in your notes, we had the standard error was, don't write it here, but we had sigma over the square root of n, right? This is the standard error from the sampling distribution, right? Okay. Can I use sigma over the square root of n here? Now I'm going to tell you no, but why not?
Because T.
Now, well, the problem is similarly back when we were doing here, the reason why we couldn't use p was because we didn't know p. Okay, what is sigma? It's the standard deviation of the population. Okay, which we don't know. We don't know the standard deviation of the population. Okay, so if we don't know the standard deviation of the population, how do we get around that?
Using the statistic, using the sample.
Yeah, we'll use the sample, so we'll take the what of the sample? We'll take the standard deviation of the sample, okay? What's the symbol we use for the standard deviation of the sample? S, okay? So I'm going to just plug in S instead of sigma, and we're going to have S over the square root of n, okay? And so here we use S, we replace sigma with S because we don't know, because we do not know sigma. Okay, we don't know the population standard deviation, so we're going to plug in the standard deviation of the sample. Okay, so our confidence interval for the population mean mu is x bar plus or minus t star times s over the square root of n. Okay. So with confidence intervals for p hat, I told you, there's like 4 values of z star that you need to know, right? That's what we said. Okay. This time for t star, there's too many to know, but they're all listed on your reference table. Okay. And so you'll see at the top it says confidence level. And there's kind of headings that say, like, if you want an 80% or a 90% or 95% or 99% or something like that, if you want a confidence level, you're going to use one of these things. And down the left edge of the table, we have degrees of freedom. Okay? So the degrees of freedom in this situation, the degrees of freedom, df, is equal to n minus 1. It's your sample size minus 1. So for example, let's say you have n equal to 15. You have 15 items in your sample, okay, and you want a confidence level of 95%. Okay? Then the t star that you would use, how many degrees of freedom would we have here? We would have degrees of freedom equal to 14, and we want 95% confidence, so I'm going to go to degrees of freedom to 14. I would go to that row, and then I look at 95% confidence, and the value for my t star would be 2.145. Is that good? Okay, so let's try a problem out here. So again, our confidence interval is x bar plus or minus t star times s over the square root of n. Okay? So here we will say, what is the average weight I don't know, of a dairy cow? Okay, so let's say we take a random sample, and I'm not sure how we did this, but somehow we took a random sample of 10 cows. Okay, and we'll assume that cows are, approximately normally distributed in weight, so we can use the central limit theorem. Okay, we'll say we can use the central limit theorem. All right, we'll say the average weight of these 10 cows is 1,460 pounds. Okay, and the standard deviation of these 10 measurements is 163 pounds. Okay, so again, just pretend like we've gathered 10 numbers here, okay, and I've just taken the average of those 10 numbers and the standard deviation of those 10 numbers, okay? So, I would have 10 numbers, but I've already boiled it down to the mean and the standard deviation for you. Okay? So go ahead and let's make a confidence interval here. Or actually, I'll just do it. Okay, so let's identify the information we have. What is the x bar?
Sample.
My sample mean 1460. What is s? 163. What is my n? 10. Okay. So what is my t star that I'm going to use? Let's say we're going to make a 95% confidence interval. So t star, I would have degrees of freedom equal to 9, 2.262, right? 9 degrees of freedom, 95% confidence. I have t star equal to 2.262. Okay. All right, so my confidence interval, if I plug all of these in, will be 1460 x bar plus or minus the t star of 2.262 times s 163 divided by the square root of n divided by the square root of 10. Okay, so this is going to give me on the low. Well, let's do the math here. We'll do 1460 plus or minus. Okay, so I'm going to do 2.262 times 163 divided by the square root of 10. So 2.262 times 163 divided by the square root of 10. Okay, I got 116.6. Okay, so I'm just going to round off to there. 116.6. Okay, so on my low end, I have 1460 minus 116.6. I got 1343.4. And on the high end, I come back here, 1460. I got low battery here. Plus 116.6. And I have 1576.6. Okay, and so now I would say I am 95% confident that the mean weight or average weight of all dairy cows in the population is between 1,343.4 pounds and 1,576.6 pounds. Okay, is that okay? All right, what if I ask, do we have evidence that the average weight is not 1,600 pounds? What would you guys say? Okay, so is your answer yes or no to this question? Okay, the answer is yes. Why is the answer yes? Because 1600 is outside of the interval. So 1600 is outside the interval. So it is not a plausible value. Yes.
So you got the low by subtracting 160 from 1460, right?
Correct.
You got the high by just adding.
Correct. Yeah, 1460 plus 116.6 is 1576.6. Okay, is that good?
Just how do you, I know the t value, the 2.262, how did you end up getting that exactly?
How did I get 2.262?
Yeah, is the degree of freedom given, right?
No, the degrees of freedom is not given. What is degrees of freedom? Degrees of freedom is equal to n minus 1. Okay, so you have to figure that out. You got n is 10, so you do 10 minus 1, and you get 9. Yes?
You're gonna give us the percent for the confidence, right?
Yeah, the confidence level for the problem will be asked of you. Okay? Okay, is this good? All right, let's take a 10-minute break here, and then we'll continue on. We'll hit up the other topic.